Welcome to Unit 7, Lesson 2, Mean Value Theorem. To understand this theorem, we will start with two thinking problems. So here is the first one. In this question, we know that Antoine is driving. At exactly 7 p.m., he is driving at 50 miles per hour. Antoine accelerates, so that means he is going faster. He is speeding up, and he is driving at 70 miles per hour at 7:02 p.m. So again, at 7, he is driving at 50 miles per hour. At 7:02, he is driving at 70 miles per hour. So 50 miles, he speeds up to 70 miles per hour. Okay. Part A of the question. What speed is Antoine driving at 7:01 p.m.? Okay. Some students might say, well, at 7 p.m. he's driving at 50 miles per hour, and at 7:02 he's driving at 70 miles per hour. So at 7:01 he must be driving at 60 because 60 is the average, the mean of 50 and 70. So that's what some students might say. However, that would not be correct. In fact, all we know is that at 7, the velocity is 50, and at 7:02, the velocity at 70. But we don't really know what the speed could be in between those two times. Let's go to decimals. So here, the y-axis is going to be the speed. The x-axis is going to be the time. I'm going to make some points. At 7 o'clock, so at x equals 7, we know the velocity is 50. So there's a point here. We know the velocity is 50 right here. That's what we're told. We also know that at 7:02, so I'm going to use x equals 7.02. The velocity, the y-axis, is 70. So we know that we have a point at x equals 7.02, y equals 70. So we know the line has to have gone up. It must go up from here to here, from the first point, 750, to the second point, 7.02, 70. The problem is we don't know how it might go up. It might go up like a straight line. Let me do this again. That's not straight at all. So it might go up like a straight line from here to here. If it goes up like a straight line, if the acceleration is constant, then yes, at 7:01, here's the point, at x equals 7.01, y is 60. That would be right. But the line does not have to be straight. All we know is that it passes through these 2 points, 750 and 7.0270. Instead, the line could go up slowly at the beginning like this, and then speeds up really quickly at the end. In which case, the speed is closer to 50 the whole time, and then it goes up to 70. The line could could go up really quickly, and then it goes up very, very, very slowly. The line could even go down at first. Maybe he slows down, and then he speeds up a lot. So we can draw any line between these 2 points can work. So we cannot say that our line passes through 7.0160. So we really don't know the speed of Antoine at 7.01. Okay. Again, all we know is the line passes through the 2 points 7, 50, and the point 7.02, 70. That's all we know. So going back to our problem, what speed is Antoine driving at 7.01 p.m.? We don't know. That's the answer. Question B. True or false? Sometime between 7 and 7:02 p.m., Antoine is driving at exactly 60 miles per hour. Let's go back to our graph. We know that our line passes through 750 and 7.02, 70. There are many lines we can draw. We can draw the straight line. We can draw many squiggly lines. I'll just draw many of them. It doesn't matter. As long as those lines pass through these 2 points, we're okay. But all of these lines have something in common. If the speed starts at 50 and it goes to 70, these lines are all continuous, right? Because Antoine's speed can't jump. Physically, that's not possible. Antoine's speed, to go from like 51 to 53 miles per hour, Antoine's speed must go through 52 somehow. So all of these lines that start at 50 and end at 70 must pass through 60. It must pass through this line. I'm going to draw this line, the horizontal line, y equals 60. That's not perfect. Let me do that one more time. So here's my y equals 60 line. And we see that all of our lines that we drew, all of the possible speeds of Antoine must be at 60 miles per hour at some point. In fact, it can pass through 60 miles per hour many times. But it must pass through the 60 at least once. So true or false? Going back to our question, sometime between 7 and 7:02, Antoine is driving at exactly 60 miles per hour. That's true. The speed cannot go from 50 to 70 without passing through 70. Okay? We know this is true because the line, which is the function of Antoine's speed, v of t, is continuous and differentiable. It is continuous. It is always, like, to draw my line, I can just draw it with one single. Let me describe this better. To draw a continuous line, I can use one pen. I don't have to pull my pen up and down. I can just draw it. So this would be continuous. I'm just drawing one line. Whereas, remember, a line that's not continuous might be here, and then it is going, and then it takes a jump. There are no jumps to these lines. Also, these lines are differentiable. In fact, mean value theorem that we will learn about, it only works if the functions are continuous and differentiable in the region we are looking at. Okay. All right, thinking question number 2. Second problem. At t equals 0, Maria is driving past a police car at 50 miles per hour. 0.5 hours later, half an hour later, so 30 minutes, Maria has traveled 40 miles and drive past a different police car at 50 miles per hour. The speed limit everywhere is 60 miles per hour. Part A. So Maria saw the police car twice. did Maria break the speed limit at t equals 0 or at t equals 0.5? Well, at t equals 0, her speed is 50. At t equals 0.5, her speed is 50 again. So no. Whenever a police car sees her, she is driving at 50. She is not breaking the speed limit. Breaking the speed limit means you're driving faster than 60. That's when the police can stop you and give you a ticket and fine you. Like, you have to pay money. So no. Part B. Can the police prove that Maria broke the limit sometime between t equals 0 and t equals 0.5? As a matter of fact, yes, the police can prove this. Why? Because the average speed of Maria, that's the average rate of change. What's her average speed? Well, speed is distance over time. She has driven how many miles? The question says Maria has traveled 40 miles. So 40 miles is the distance. How much time happened? 0.5 hours, because from t equals 0 to t equals 0.5, the time elapsed, the time that has happened, is 0.5 hours. 40 miles divided by 0.5 hours is 80 miles per hour. On average, she is driving at 80 miles per hour. Why? Well, we can think of it this way. The average speed is 80 miles per hour, right? Well, if Maria is driving at 80 miles per hour in the entire interval, this is actually not possible because she's at 50 at t equals 0 and at 50 at t equals 0.5. But we'll just assume that she is driving at 80 miles per hour in the interval in between, and her speed somehow takes a jump from 50 to 80 at t equals 0 and back to 50 at t equals 0.5. Well, if that's the case, then she broke the speed limit. Her speed is 80. Okay? But you might say, okay, maybe she didn't drive at 80 miles per hour the whole time. Maybe at some point she's going slower. She's not going 80. She's really only going at 55. That is not breaking the speed limit. The problem is if she is going below the average speed at some point, she must be going above the average speed at some other point in this interval. That's the only way for the average to be 80. So, in other words, if the average is 80, at some point, she has to be driving at 80 miles per hour. 80 is higher than 60. So, yes, Maria has broken the speed limit. So, what the police is saying is, given that her average speed during this time interval is 80, there must be some point in time in which she drives at exactly 80. That's the only way for the average to work. Or she goes faster. But again, we know that if she drives slower than 80 at some point, she must drive higher than 80 at some point. And if her speed cannot take jumps, the function is continuous and differentiable, no jumps, then it must be passing through 80, which is what we learned in our last problem. So there must be some point in time in which she drives at exactly 80. So yes, Maria broke the speed limit. Okay. What did we learn? We actually learned the mean value theorem. The mean value theorem says this. Given a function that is continuous and differentiable, in fact, it only needs to be continuous and differentiable in that interval, including a and b for one of them. But let's just say the entire function is continuous and differentiable. Then, in the interval a, b, in our last problem, the interval is 0 to 0.5. We just write it this way, interval parentheses a, b, close parentheses. In this interval, there must exist some point c, so c is in between a and b, such that f prime of c equals fb minus fa over b minus a. What does that mean? Well, fb minus fa over b minus a is just the average rate of change. F prime of c is the instantaneous rate of change. So in other words, the mean value theorem says that if the average rate of change between a and b is x, then there is some point c inside a and b, inside the interval a, b, such that the instantaneous rate of change at c is also x. Okay? So if the average rate of change is x in an interval, there must be some point in that interval where the instantaneous rate of change, the derivative, is equal to the average. When we apply this to Maria's example, what we're saying is if the average speed is 80, then 80 is x. So there must be some point c, and really some time, it's really time. There must be some time c between the two police cars that she is driving at exactly 80 miles per hour. Given that, her speed is in fact continuous and differentiable. All right. Let's look at a graph to help us understand this better. Here we have a graph of some function. It's a parabola. It starts at x equals a. It starts going up, 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 up. When it gets to x equals c, it is horizontal. And then it starts going down, 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 and more down. And it stops at x equals b. So c is in the interval a, b in this diagram. Also, we know that fa is equal to fb. The graph started and ended with the same y. If I draw a line in between fa and fb, so let's do that now. I'm drawing a straight line between fa and fb. There's a name for this line. This line is called the secant line. Secant as in like cosine, cosecant, secant from trigonometry. This is called the secant line between A and B. Because FA is equal to FB, this line is horizontal. It's flat, it's not going up, it's not going down. Well, this graph, our graph in red, is continuous and differentiable. It's a parabola after all. So there must be, because FA equals FB, the secant line is horizontal, there must be some point FC, and FC is right here. It's actually the vertex of the parabola. There must be some point such that the slope at that point is 0, because our secant line has a slope of 0. The average rate of change is 0, so there is some point in between where the instantaneous slope is 0. This is actually called Rawls' theorem, but the name is not important. Rawls' theorem is just mean value theorem when the average rate of change is 0. So it makes intuitive sense. If we have 2 points, average rate of change is 0, there's gotta be some point in between where the slope is 0. But that's not the mean value theorem. The mean value theorem applies to any average rate of change. Now here's the cool part. Here's my graph. I'm going to rotate this graph, the whole graph, to the left. What happens when I rotate this graph? The average rate of change is no longer 0 between the 2 points. There's a slope. Here's the new secant line. The slope is clearly not 0. I have rotated it such that the secant line has some positive slope. But that doesn't change the fact that some point C between A and B, at some point C, the slope of our function at C must have the same slope as our secant line. In fact, this graph draws the tangent line for us. The tangent line makes it more clear what our instantaneous rate of change at x equals c is. And we can clearly see from this graph that the slope of the tangent line is equal to the slope of the secant line. So that's true for any average rate of change. So this graph shows that mean value theorem is true. Given any average rate of change between 2 points, there's some point in between where the instantaneous rate of change is the same as the average rate of change in the interval. Okay. All right, let's move on to some examples. 2 examples. Example 1. This is a question that looks like an AP calculus question. F of x is a function that is continuous and differentiable in the interval open bracket a, b, close bracket. That means this is an interval from a to b, including a and b. Which of the following is true? Statement 1. If f of a equals f of b, then there exists a point c in a, b, such that f prime of c is 0. Well, if f of a equals f of b, that means the average rate of change from a to b is 0. It's just like the graph we started with in the last slide. Fa equals fb. And we saw from the graph that there must be some point in between with slope 0. Again, this is just Rawls' theorem, so this statement is true. I'm going to put a check next to it. By the way, a good strategy for standardized tests is, now that we know statement 1 is true, we can go to our answers and eliminate the ones that are not right. There are 5 answers in AP tests. A says only 1 is true. Okay, well, we know 1 is true, so A might be right. B says 1 and 2 is true. That might be right. C says 1 and 3 is true. That might be right. D says 1, 2, and 3 are all true. That might be right. E says none of the above are true. Well, we know 1 is true, so E is wrong. Okay, statement 2. If FB minus FA equals 0, then F prime of x equals 0 in the interval AB. This looks similar to statement A. FB minus FA equals 0 just means, once again, the average rate of change has to be 0. But be careful, it says f prime of x equals 0 in the interval AB. That means that the slope is 0 everywhere in that interval. And we know that's not true. This is like our first example. Just because Antoine is driving at 40 miles per hour at A and 40 miles per hour at C doesn't mean he is driving at 40 miles everywhere in that interval. So 2 is false. Statement 2 is false. We go to our answers. A says 1 only. Maybe. B says 1 and 2. Well, 2 is false. So C says 1 and 3. D says 1, 2, and 3. We get rid of that one. Again, we can get rid of all the answers that says 2 is true. Finally, statement 3. We have to keep going because we have 2 answers left. A says 1 only. C says 1 and 3. Okay, statement 3. If FB minus FA over B minus A equals R, then there exists a point C in the interval AB such that f prime of C equals R. FB minus FA over B minus A is just the average rate of change. That's R. We know from the mean value theorem that if the average rate of change is R, then yes, there is a point at x equals c such that the slope is r, the average rate of change. This is just the mean value theorem. So C is true. Given that C is, not C, statement 3 is true. Given that statement 3 is true, A is wrong, and C is the correct answer. Okay. One more example. Example 2. F of x is equal to 3x squared minus 2x plus 5. A. Find the average rate of change in the interval 2 to 6. Alright, well, average rate of change was one of the earlier lessons we learned. That was 2.1, lesson 2.1. So if you don't remember, you can go back to that lesson. But the average rate of change is just FB minus FA over B minus A. So we'll find the slope in between those 2 points. Slope of the tangent line in between those 2 points. So it's really f of 6 minus f of 2 over 6 minus 2. Okay. If we plug them in, f of 6 is 6 squared times 3. 36 times 3 is 108. Minus 2 times 6 is minus 12. 108 minus 12 is 96. F of 2 is, 96 plus 5 is 101. So f of 6 is 101. Next, f of 2. 2 squared times 3 is 12. Minus 2 times 2, so minus 4 gives us 8. Plus 5 is 13. So it's 101 minus 13 divided by 6 minus 2, which is 4. So that's 101 minus 13, which is 88, divided by 4, which is 22. So the average rate of change of f of x is 22 in this interval. Part B. Show that there must be some point C in the interval 2, 6, such that f prime of C equals 22. Well, that's really just the mean value theorem. We know that f of x is continuous and differentiable in the closed interval 2, 6, so including the points 2 and 6, because it's a polynomial. So by the mean value theorem, C exists. That's it. we can just say the mean value theorem says it's true because our function is continuous and differentiable. Well, if it exists, part C says find C. Let's find C. Okay. Well, we know that f prime of C is 22. So let's take the derivative of our function. The derivative of 3x squared is 6x. The derivative of negative 2x is minus 2. The derivative of plus 5 is 0. So f prime of x is 6x minus 2. Therefore, f prime of C must be equal to 6 times C minus 2, which is equal to 22. We know that from part B. When we solve the equation 6c minus 2 equals 22, we get 6c equals 24, so c equals 4. So the mean value theorem says c exists, and we just found that c equals 4. So let's summarize. The mean value theorem says that if f of x is continuous and differentiable really in that interval, including a and b for one of them, then, well, for, again, as long as it's continuous in AB, including A and B, and differentiable in AB, then there exists some point x equals c inside the interval AB, not including A and B, such that the instantaneous rate of change, f prime of c, is equal to the average rate of change of that interval, fb minus fa, over b minus a. Okay? So that's it for this video.